All right, let's move to our next presentation, and also from University of Technology Sydney, UTS, and it's Dr. Andrew To, and he will deliver a presentation, the SPIR, SPIR, and autonomous underwater robotic of the bridge part cleaning and condition assessment. I think Dr. Tu is the research and development engineer in the UTS Center for Autonomous System, I think. Is that correct?
That's correct. Thank you, okay. Professor Lee.
Let's head over to you now.
Thank you very much. Thank you guys for your time. As I've been introduced, my name is Andrew To, and I'm a research and development engineer. It's my pleasure here to give you a bit of a update on what we've been doing in terms of robotics to deliver the different sensors and maintenance work to hard to reach spots in bridges. Okay. So we've done quite a few robots on the Harbour Bridge, and I'm just going to give a quick refresher on the different motivations and areas we've tackled with the Harbour Bridge. We've done the archway. So in previous, I believe we presented some robotics work on robots for climbing the arches of the Harbour Bridge. As you know now, it was developed in the bridge was made in the 1930s, but OHS have said that it is quite dangerous to put humans into these archways now. So robotic solutions are the path to go. And we've been working since 2012, I believe, on developing robot systems to go in there and inspect, and then do some maintenance work if there is rusting or other things inside. We've done robots. That's the first versions that we've worked on, is the underdeck of the Harbour Bridge. So typically they put humans in there to do sandblasting, and there is asbestos and lead-based paint. So it was a perfect case to put robotic systems in there to take humans out of that loop. And the particular talk we're going to focus on is an update on the work with underwater, not particularly about just the Harbour Bridge, but all the bridges in that is managed by Transport New South Wales. I'll just sidetrack a little bit to give a bit of an update also on the climbing robot, because I think there is a bit of interest from previous presentations. So as you know, it's quite challenging to get sensors and inspect these areas. These are some of the photos to show what a human has to go through to get the assessment done for those archways. So we've in previous built a magnetic foot pad based robot. That was good for taking cameras in and out of the archway to get some camera data and do some inspections. We've since moved on to scissor lift push pad based system, because they've said, great, you can get some photos, but what happens if we need to do some maintenance work? That is the new challenge that we've been tackling with RMS, is that how can we get a robot that is strong enough to traverse through these archways and deliver, say for example, a tiny pencil tip spray sandblasting gun to clean away the rust necessary. So just some videos just to give an update about what we've been doing for that aspect. So this has wrapped up. We've given this robot to RMS for use. This was finished off last year. So just let this video run off a little bit longer. So this was in a section of the Harbour Bridge archways. Okay, back onto topic. So the particular project that I wanted to talk about is also working with Transport of New South Wales. They have contractors that flows down to Downer Mutual, and then they subcontract down to the actual diving companies such as HDSA. Those are our main collaboration partners. It's a big team. From the UTS side, you can see it's led by Professor Dikai and Professor Gamini Disanyaki, and then we're all the other staff in terms of providing the engineering, the know-hows of doing the algorithms for localization and mapping. That's what the center is known for. Okay, So the big challenge with bridges, as opposed to archway, is we're looking at the problem of the piles, the poles that are holding up the bridges. So they need to be regularly maintained. If they're not well looked after, they will corrode and deteriorate, and then you'll have structural failures. And this is a big problem because these are amenities that are depended upon by the public. So if we have a bridge that is, say for example, decommissioned for a period of time, then it will affect whatever traffic flows there. So there's a good spotlight put on to maintaining them. And particularly just looking at New South Wales, there is maybe I think 4,000 bridges, 4,700 bridges that just the Transport of New South Wales looks after. And in all of Australia, about 50,000, and many, many more as you take it globally. You scale that into the space of, say, for example, other infrastructures like Wharf, Port of Brisbane, Port of Melbourne. They have roughly around 50,000 piles to hold up their structures as well. So those are all the scale of work that we're looking at to address with this particular robotic challenge we're doing. Okay, so here's the thing. What's been happening now is there is inspection work that needs to be done. Typically what we do is we have to send a dive crew. It's a 4-man dive crew to dive, rotations, 1 dive master to make sure safety is looked after, and 1 boat operator. So typically a person has to jump in, go down there with cameras and needle scaler to make measurements to generate reports that they give to RMS to make assessments of whether they should proceed further with this bridge needs maintenance, or this bridge can be used for another period of time before we need to do maintenance on it. It is quite a time-intensive problem where you can't look at all the piles. You have to be selective and make spot checks. Good and bad, because that's the resource we have currently. It opens up new opportunities of whether we can develop robot systems that allows us to inspect more extensively now. The first problem that we're trying to address is it's quite dangerous. So in statistic terms, there's about 10 fatalities per 100,000 dive workers. Slightly lower than farmers. Farmers are sitting around 13 per 100,000. So it's still quite dangerous in comparison to, say, for example, you and I, who are sitting in office, we're expected maybe 1.6 per 100,000. Reasons for why it's so dangerous is that they're working in very poor visibility. They're operating equipment that are high pressure, such as a water jet, and it's also working in very awkward poses. So just may I highlight the bottom video, where that's a video from Pete's Ferry Bridge, where you've got a dive personnel holding onto the bridge pile and then holding a high pressure gun to try to clean away the barnacles so he can go and inspect the concrete work underneath. The last point I raised was something we picked up from other ports, where not particularly in Sydney, but we're looking at Northern Territory, where there's a lot of marine life that are dangerous to humans when you go down and do inspection work. So more the reasons to put a robotic system to take a human away from these dangerous situations. Let's have a look at the current state of art of what's available to do the job that I just mentioned. So we've got very custom tools where you have to set it up on a pile, and then it does it very autonomously, but it takes a lot of work to set up. So it's not very flexible to deploy. We've got a bunch of ROVs. You've got a joystick, and then you drive it around as if you were controlling a drone. So it's still quite expertise oriented, where you need a lot of training and you need to know how to use the system. So what we're doing in CAS is, can we push the boundaries of making something easy to deploy, and also a high degree of autonomy where you don't need to train the operator as much. An existing dive crew can take this bit of equipment and use it to get meaningful productivity out of it. So that's what, this is the solution we came up with. We call it SPIR, for submersible pile inspection robots. It's about 70 kilos. It can be deployed by 2 people. We have a crane on the side of the boat that is typically used for dive maintenance, and we winch it down, and then we power it up, and then basically we are able to press a go button, and then it's supposed to be able to figure out what to do and do it all autonomously. So very minimal human involvement. So I'll just go down the steps of functionalities of how we do this in the process. So this is just showing you the deployment phase, where we drop the robot into the water. We investigate the different sensor package necessary to realize this aspect of autonomous navigation. So coupling sensor fusion of SPIR and sonar, so that the robot, once deployed, it can lock onto underwater structure and then autonomously drive towards that structure. The next aspect of maintenance is, because we're working high current flow, we needed to address the problem of how do we stabilize the robot to either do maintenance work or do collect visual data. So the very obvious thing was that we adapted what a human would do, is that when they do work, they wrap a big tether cord around the pile and then they lean against it. So we've taken inspiration for that, and we've developed what we call claw arms. Essentially, it's a set of arms that clamps tightly onto the structure, so that the robot is now rigid with the structure. So it's quite adaptive. The range of what it can grab ranges from 600 millimeter diameter to down to maybe 300 millimeter diameter. And depending on if it's a bigger structure, then we can put bigger arms for that purpose as well. So it's quite adaptive for the application space. So the next part is applying what the center's research into this domain. So there's a lot of PhD and master student work involved in this section, where we collect sensor data, and in the domain of underwater vision, how do we build a map of the structure so that we can register captured images to it, and also be able to build a point cloud so that we can make a deduction of what is marine growth versus the core of the structure. So in that way, we can intelligently plan what areas to clean and be more effective in the cleaning process. So cleaning is achieved with a 3-degree of arm that sits on top of the robot. We've adapted what a cleaner would usually use, is a high pressure turbojet nozzle onto this system. So it's delivering 4,000 PSI in a very streamed high pressure jet onto the surface. And then that removes the barnacles so that you reveal the existing concrete structure below it, so that you can capture visual images later and perform inspection work. So this is the last part, where now that we've removed the marine growth, we are able to dock on again and get visual data. So being able to grasp tightly allows us to get very high quality image data, and also reduce the noise, because we're establishing a rigid, it's like a tripod, where a lot of the gunk can be processed out by stacking multiple images together to remove noise. So that's some of the techniques we try to generate high quality images out of this. And because we've also built a 3D map, and we can register these images to those 3D maps. So we know exactly where they've been taken and what days they've been taken. So it builds an asset registry of, if we were to revisit in 2-3 years, we can pull up those data sets again and then make a comparison. So that's the gist of what this presentation is, to give an update of what we've done in this domain of bridge maintenance for underwater work. We've done various trials within the period, where we had a ASE linkage grant from 2016 to 2019. We visited mainly in the northern beaches, the Pete's Ferry Bridge, the Mullet Bridge, and the Narrabeen Bridge. We did go south to Windang Bridge. So each bridge presented new challenges that we had to make modifications to the robot and adapt the algorithms to deal with these conditions. So that was a very interesting bit of work. We've had good feedback from the industry in terms of we are working closely with the dive team, so they are getting good exposure to what is leading edge research and giving us on the ground feedback of what they want and how it should be made easier for them to use. Okay, do we have any time for maybe one question or two questions?
Oh yeah, definitely. I mean, I think thanks for a really exciting presentation. I'm sure anyone, many people interested. Let's give a chance. You're just on time. So so anyone have a question, please just go ahead. It's just wonderful.
In the Q&A slot, you'll see a question for you from John.
Okay.
Right, okay. How efficient is the robot relative to human? I'm going to say we're not going to beat humans because humans have the abilities to reach around and clean certain sections of the barnacles that it just drops a whole chunk out. So that like with that ability and dexterity, we're not going to be able to beat a human with a 3-DOF arm. In saying so, we're not trying to compete with a human because we're trying to expand on what a human can and can't do in these situations. For example, the safe operating procedure does say that a human shouldn't go down and do maintenance work in 1.5 knots of water current because it's just too difficult to swim against and come back onto the boat. So if the robot is able to be deployed from that space onwards, then we are giving more capabilities to a human dive team. So we're not beating a human in that sense. Okay, so got another question. Thank you for your presentation. What is the best method to update FB with field tests? Mac normally is hard to match. Does Mac curvature give better results? That's beyond my area of expertise, so I'm gonna have to say I can't give you a proper answer to that question. I see there's a fair few response to that already because I'm a mechatronics engineer, so that aspect of the research I haven't been well versed against. Sorry for not being able to provide a good answer for that. Okay. There's one more question. So how to ensure that the removal of barnacles is not cause of the damage to the part? I had some experience in this regard. So again, it is experience, and we do start with a more conservative approach, meaning that we have got feedback from a human dive team of what should and can't be done for different bridges. So we go to a bridge and then they say, you shouldn't use this turbojet nozzle or this kind of pressure. So it's getting those kind of feedback. And also we take a very conservative approach of we start very far away and then slowly go in. And then as we go in, we make visual confirmation that this setting is suitable for that part. So we haven't had damage to a bridge structure before, but I did make a hole in one of the brick walls in UTS. I'm not going to tell where because that's I plead the fifth.
Andrew, I do have a question for you.
Yes.
Have you worked on any like a wharf or the timber type of the pile so far in your project?
Right, okay, so we were going to schedule a visit down to Port of Melbourne to do the wharf piles, but we haven't had an opportunity due to COVID and just lining things up. In one of the bridges we went to was Windang Bridge. They had a decommissioned bit of pile, from a timber pile. We did hit it with the water jet and it looks fine. There's no notable structural damage from the timber itself.
Thank you very much. Okay, I think it's really interesting and you can see a lot of questions come toward you. Thank you very much, Andrew, and for your wonderful presentation again. And with this one, I think we would like to close session. And before that one, I would like to thank all the presenter and also audience and interestingly asking questions. So very well done. And so with that, let's conclude this session. Thank you.